Sí se puede.
¿Ya? ¿Se puede?
Ya, entonces, bienvenidos al seminario del Instituto de Ingeniería Matemática y Computacional. Federico Fuentes, quien es habitualmente el anfitrión del seminario, hoy día no pudo estar de forma presencial, así que voy a introducir yo a presentar al expositor del día de hoy. Hoy día nos acompaña Pablo Barceló. Si alguien no lo conoce, Pablo es profesor titular de la universidad y además es director del Instituto de Ingeniería Matemática y Computacional. Pablo además es uno de los investigadores principales del Centro Nacional en Inteligencia Artificial, el proyecto CENIA, que está albergado en la universidad. Pablo obtuvo su doctorado en la Universidad de Toronto. Él trabaja en temas relacionados con lógica y teoría en ciencias de la computación y sobre todo las líneas emergentes que existen en las conexiones de estas áreas con Machine Learning. Así que Pablo creo que hoy nos va a hablar algo un poco de esos temas. Así que, Pablo.
La verdad que no, gracias, Carlos. Quiero presentar un resultado que es un resultado que apareció en teoría de base de datos, pero que en realidad está súper relacionado con ciertas desigualdades entrópicas. So, do you want me to speak in English there?
Up to you. I mean, the slides are in English, so whatever
I
you
think
want.
it's fine. Yeah. So everybody's fine if I speak in English? Yeah? Everybody are. Everybody are fine. So that it has to do with some entropic inequalities, but that it has a lot of applications in computer science. Right? So as you will see, the result, the inequality that I'll present is nothing else in the end that one of these entropic inequalities, which is shaded. I said that I was going to present the proof based on holders. But after all, I realized that it's simpler to present it in terms of shaded. So that's the one that I'm gonna give today. The one based on holder, the proof based on holder, also yields an optimal algorithm for evaluating certain things. But since we are not paying attention to that today, I think it's better to present this. So let us start with the following question. Imagine that you have a graph, yeah, simple graph, and you have n edges. How many? It's a directed graph, right? How many directed triangles can you have in this graph? Yeah? I don't want this to be a quiz because I know that it's not an easy question, and if someone can answer right away, it's probably because they know the answer already, like Domagoj here. But the answer is quite surprising. It is like this. ¿Cero? Está como pegado.
Probablemente está tomada la pantalla de Zoom. ¿Quieres volver a...
Ah. ¿Qué cosa es eso? Yeah. Gracias. So that's the answer. It's n to the 3/2 thirds. Yeah. I don't know any simple way to explain why this is the result.
Sorry, how many vertices do you have here?
It doesn't matter. I mean, it only depends on the edges in this case.
You choose as many you can make them as small as you want, like a small click or a large.
It's just a triangle, no? It's a directed triangle. Yeah, the thing is that if you have n edges, the inequality says that you can have at most this number of triangles.
No matter how many vertices.
No matter how many vertices. So, and this was proved in a stock paper years ago, and it was considered to be a groundbreaking result and so on. And what I'm going to present today is actually the AGM Bound, which is a generalization of this result.
¿Es it optimal or asymptotic?
No, it is optimal. The AGM Bound is optimal in the sense that you can always construct graphs for which this bound is achieved. That's why it's so powerful. Yeah.
And the graph that achieves it is a click where you orient always to the larger one, or what's happening? No?
Domagoj knows better probably about the lower bound. How is the graph?
No, I think the lower bound is you take square root of n something like this. They all go to 1.
Yeah.
I mean, there is this image by Hund, no? That's very explanatory, but it's a bit like you're trying to, you can think of this as you're filling end positions for the edges with nodes somehow. So you take something like square root of m on one side, square root of m on another, and trying to connect.
We can, but yeah, I can point you to something where
you don't have that many vertices, roughly.
No. It will probably have 3 square root of n vertices, something like that. I mean, the bound is actually stronger now. It says, give me any m, I can find you a graph with some very limited number of vertices, which is like square root of m something.
Yes.
The vertices where this bound is achieved exactly.
Only for this number of vertices, or is there other vertices?
No, but if you add more, then you still have the bound more. But this is the minimum number.
Dieter, let's, I can, yeah. In any case, my talk is not very long, but I would prefer to, then we can discuss all the time we want. Right, so what we will be considering is edge label graphs. Yes, this result actually extends to arbitrary relational structures for those familiarized with first order logic, for instance, yeah? So, but for us, and for simplicity, and for visibility, and for ease of, understanding the results, I'll focus on edge label graphs only. So we have a graph, G, which consists of a set of vertices, B, a set of edges, E, and this labeling function that labels each edge with a subset of some letters, yes, from a finite alpha. For instance, here we have this graph, and it's not directed. We don't need it to be directed since we have the edge labels, and with the edge labels we can encode directions. So this edge here is labeled with both A and B, this one with B only. We will assume that each edge is labeled with at least some letter, but it can be labeled with more than one letter. And we will be interested in the notion of homomorphism from a label graph, an edge label graph into another one. Let me quickly remind you what is this. The homomorphism from H to G is nothing else than a mapping from the set of vertices of H to the set of vertices of G that preserves the adjacency relation. Each time we have two nodes that are adjacent in H, their images are adjacent in G. And the labels of an edge, the set of labels of an edge is contained in the set of labels of their image. Yeah, so it doesn't need to be the same set of labels. It needs to be contained. Yeah. So from now on, we will write hom of HG for the set of all possible homomorphism from H to G. Yeah, and here, for instance, we have a homomorphism, right? So I can fold this here, yes, but something will be lacking, right? Because this is labeled AB. If I fold this here, this is only labeled B, it's not sufficient. So I will enlarge this with A and B. So there is a homomorphism from this graph into this graph. And you can see that there is no homomorphism in the opposite direction, no? Yes? Good. So what is it that we want to determine? We want to determine an upper bound on the number of homomorphisms from H to G. Later, I will connect this back to the original question of how many triangles, no? But we are gonna count the number of homomorphisms from an edge label graph H to an edge label graph G. And for simplicity, we will assume that the graph H is what we call a graph pattern. In the graph pattern, each edge is labeled with a single letter. Not in G. In G, we allow edges to be labeled with several letters. The result is independent from that, but the presentation is simpler this way. And in most of the cases, the kind of applications that we will consider or that we consider in computer science only have one letter in the pattern that we're trying to find into G. right? This H. So in patterns, the important bit is that there is a one-to-one correspondence between the edges of the pattern and a subset of the symbols of the alphabets, right? Each edge is labeled with some symbol, and no two edges are labeled with different symbols. So I don't know if I was clear enough. Each edge is labeled with a different symbol from the alphabet. That's what I wanted to say. Not only with a one, but with a unique, different from the other edges, right? So let us consider pattern H. The bound that we are gonna construct is based on the notion of a fractional edge cover of H. What is a fractional edge cover? It's a relaxation of the usual notion of edge cover. So it is a function that assigns to each edge in H a rational number, a positive rational number. Yes? And such that for each vertex, B, the number of edges that touch B, if we look at the value of those edges, sum up to at least one. Yes? So we're saying that each vertex is covered in the sense that the sum of the edges that touch this vertex, their fractional values sum up to at least one. So what is a relaxation of edge cover? In edge cover, we assume this function to be either 0 or 1 in its value. Yes? And we want each edge to be touched by at least some, each vertex to be touched by at least some edge that has value 1. Here there is an example of a fractional edge cover. No? It is a triangle. This is the pattern. It's a fractional edge cover of this pattern in which each edge takes value 1/2. Yeah. So this is covered by this plus this, 1, and same for all the other vertices. This is a possible fractional edge cover. But there are also other fractional edge covers. No? For instance, I can take value 1, 1, and 0. Yeah? So what is the best fractional edge cover? It will depend on the graph G to determine my bound. But we haven't said what is the bound yet. So now I will present what is called the AGM bound. There is this bound by Atserias, Grohe, and Marx. That's why it's called AGM bound. So we will use some terminology. Isabay of G is the set of edges labeled A in G in the graph where we're looking for the homomorphic images of H. Then we assume that we have a fractional edge cover, some fractional edge cover of H, which is this mapping F. And finally, we will denote in this way the edge, which is labeled A in H. Remember that each edge is labeled with a different symbol, so this is uniquely identified. So what does the AGM bound says? It says the following. The number of homomorphisms from H to G is bounded by the productory of, for each symbol that appears in H, take the number of edges labeled with that symbol in G, and this is to the power of the value of the fractional edge cover on the edge label A in H. Yeah, we will see examples later. So questions up to here?
It doesn't matter for the fractional edge cover of H. It could be.
It could be any. For any fractional edge cover, this is true.
Okay.
Now, what is the best bound depends on G.
Of course.
Yeah, that's the idea.
On G.
On G, right? Because that's the thing. I mean, when we say that this bound is optimal, it's optimal with respect to the best fractional edge cover for G. We will see why the size of G matters, right? But in the end, for instance, if this value, if you have lots of edges labeled A, you would like to take that small value on F, right? That's the idea. ¿Segundo?
Sí. No sé si me queda antes, pero esto es como una generalización de la desigualdad de Scherer, como no uniforme, no ocupar K-cover, sino que...
Es esencialmente la desigualdad de Scherer. O sea, cuando...
¿O es más?
Yo diría que es. Cuando veamos la demostración, en el fondo, la desigualdad de Scherer es también muy parecida a Loomis-Whitney, ¿no? No sé si...
Estamos en inglés. Perdón.
Sorry. Scherer's inequality is very similar to Loomis-Whitney, and what it does is to project a probability value from a set of variables into its different projections. Let's see the proof later, and you will see that it's essentially the same. But the application is beautiful, no? So, for instance, take this fractional edge cover of this triangle with A and B and C. What is the maximum number of homomorphisms from, sorry, what is a bound on the number of homomorphisms from H to J? It's, in this case, number of edges labeled A times number of edges labeled B times number of edges labeled C squared. Yes?
G is the triangle.
No, H is the triangle.
Who is G? Who is G?
Any G. For any G, this holds. Yeah, so take a G. Yeah,
that's the number of A's in G.
Yeah, this is the number of of A's in G.
Okay.
Right?
E prime is of H.
Yeah, this should have a G here. Yes, so in H, there is a single one. There is a single edge label A, right? But in G, there can be many. So H is considered to be a small pattern and G to be a huge graph, right? That's the difference, intuitively, no? So in H, you have a single edge label A. In G, you can have many. M, for instance. M1, M2, M3. Yes? And this is squared. Yeah?
And how sharp is that bound?
Sharp.
It's optimal. Yes. There are. Yeah.
So for any H, you can find the covering that gives the optimal value.
For any fractional cover, that's, yeah. Domagoj actually knows better than me than this because he has worked with this bound. He probably knows better the lower bounds.
Yes, but it's a bit more tricky, but essentially it's up to, look, it's basically, let's assume that they all have the same cardinality. Then you can say, give me an N, I can find you an instance where the bound is sharp. And this holds for particular edge cover for which there is an algorithm how we find it.
Yeah.
I mean,
The problem is when the different A, B's, and C are skewed, no?
Yeah, then it's all a mess.
Yes.
So that algorithm produces one with the smallest possible fractional.
Yes. And I don't know if Pablo is going to get there, but you do it by solving the optimization problem.
No, I will not get there. I just want to show the bound and provide a proof. But as you can see, I mean, this is a possible bound, but it depends on the data, depends on the G, whether it's a best bound or not, because you have a different bound, no? You have this one. And depends on the graph, whether this is better or not than the previous one, no? So for instance, if C is very small, the number of edges labeled C, you might want to use this one, no? But that's the idea, right? So for each fractional edge cover, you will have this this upper bound. Yeah? So this is used, for instance, for evaluating queries in databases. The query is the pattern, and then you want to know how many answers. The homomorphic images of this query are the answers of your query, right? And then you want to upper bound the number of possible answers. Yeah? But not only that, you want to compute them, no? And you want to compute them efficiently, and this bound somehow gives you hints on how to compute them efficiently. So now let's go back to the original example. Imagine that so we don't mind about the letters. The letters, we just use them as an artifact. All edges in the graph G are labeled with A, B, and C, right? So I can map this into any triangle in the underlying graph. So what is the number of homomorphisms from this H to the graph G? Well, it's 3 times the number of triangles in G. Why 3 times? Because I can homomorphically map this in 3 different ways in each triangle, no? Yes? And then we go back to the inequality, right? So this is M, yes? M squared, M cubed, M to the 3 half. Yeah? I've never learned arithmetics in English. I don't know how to. M to the 3 half. Yeah, and since it is 3 times the number of triangles, it will be n to the 3 half sets. Yes? Do you believe me? Or more than believe me?
I think you have a type.
Where?
I think it's 3M and AGM are all M.
No. M is the number of edges, no?
Yeah.
All edges in the underlying graph will be labeled with A, B, and C.
Yeah.
So you can map this into any possible triangle.
You're just giving the bound. Okay.
I'm just giving them. Yeah. Okay, so proof of the AGM bound in 5 slides. And then we finish and we can discuss. So we have a graph pattern H, a graph G, and we will define a random variable. What will be the range of these random variables? It will be all possible tuples of size number of nodes in H, yeah? Of nodes from G. So these are the possible values of the homomorphisms. No? Each homomorphism maps the nodes of H into the nodes of G. Yeah? And we will define it in the following way. If B is not the image of some homomorphism, then its probability of the random variable to take value B is simply 0. Else is the uniform distribution on the ones that are images of some homomorphism, right? Of course, computing this is very expensive, but we don't want to compute it. We just want to use it. So here there is a typo, of course. The value of the entropy is not the expected value of minus log x but minus of log of the probability of x. Yeah? But in any case, what it will be in this case, the entropy of this random variable, it will be the sum over those values that are different than 0. That is the tuples that are the image of some homomorphism of what? Its probability, 1 divided by this, times log of this probability. The number of tables in which you have this is precisely this, and then you have this minus outside, so the log is inverted. That will be the entropy of this random variable, right? It will be log 2, log of the size of the thing that we want to estimate. And here comes Schiller's inequality. What Schiller inequality says? It says the following. If we have a random variable that is the joint of distribution of all these variables x sub I, yes? And we have n subsets of I, not necessarily distinct. And we know that each I from the index set I appears in at least k of these sets. And we denote in this way the marginal probability defined by the x sub i's with I in A sub j. Then if you sum the entropies of the marginal probabilities of the A sub j's over all of them, if you sum this will be at least k times the entropy of the original value. And it is very easy to prove this inequality. Yeah, it's a very powerful inequality, but it's quite easy to prove. Yeah. You don't believe me, Tomás?
No, I never seen this version. I just know the one from information theory where it would count the number of bits. I mean, it's probably the same thing. It's just a combinatorial proof where you like have a binary number, you fix one, and then you know how to sum over the rest.
Okay, yeah, so I think it has a similar thing.
Is there a beautiful proof to see this? Like just
No, it is very beautiful. It's very simple.
Yeah, it's very elegant, but it's like this difficult combinatorial part. When you fix the coordinate of a binary number and sum over you get one.
No, yeah, actually, it's just, I mean, like what you see here is you're trying to have a bound on the entropy of this based on the entropy of the projections. No? That's what Schiller is saying. And so then you express the entropy of this based on, well, this will be the entropy of X is the entropy of X1 plus the entropy of X1 given X2 and so on, no? And this can be expressed in similar way, but depending just on the indexes that they mentioned. So then you sum all these things and they cancel out somehow, right?
But is this the same intuition like this? Because I don't know the proof of the full inequality, just the one they need for AGM, which is that, I mean, the minimum number of bits you need to represent a certain value is the entropy of this thing, and then how do I get it? Well, if I know some value, then I sum over the rest, and then that's it.
Probably, I don't.
I think the same proof.
I think it's the same idea, yes. Yeah. But in the paper, they refer to this other proof. They say there is a very simple proof in this place, and I went to see it, and it's essentially what I'm saying, this cancellation.
No, but
okay. Well, this is Schiller's inequality. So the only thing that we will use aside from Schiller's inequality is that the entropy of a random variable is maximized when the probability distribution is uniform, in which case it takes value log of. Yes. So we will assume that we have our fractional edge cover. All of them have the same, we have relativized this to have all of them the same denominator Q. And we will apply Schiller's inequality with I equals B prime, the set of vertices, and we will have P sub A copies of each edge, which we know that each edge is a subset of size 2 of this B prime. And we will have P sub A copies where P sub A is this value here. Yeah. So what happens in this case? Well, we're applying in this way. Every B prime in every node in the pattern belongs to at least Q of these sets. Why? Well, the number of sets containing B prime is what? Is P sub 8 times, because I'm amplifying the number of times a set appears, P sub 8 times. The A's such that B prime touches the edge A in H. And by definition, P sub A is Q times the number, Q times the value of the fractional edge cover. Yeah, but this is the sum of all this. And what is this? The sum of the value of the fractional edge cover for a B prime over all edges that touch B prime, right? But we know that since it is a fractional edge cover, this value is at least 1, no? Yeah, so this is bigger or equal than Q. So each node from H appears in at least Q of these sets once we amplify. Yeah? And as a corollary, what we get? If we sum, if we sum over all edges of H, P sub 8 times, because that's the number of times the number of times we have replicated this set. The entropy of this variable, it will be at least Q times the entropy of this variable. Yeah? Sorry. It's clear? Inequality? Yeah. So what's the other observation? The marginal distribution on each edge of this is 0 in every tuple that is not an edge. Yes? Why? Because if it is a homomorphism, it has to be an edge on each one of the edges of H, right? And what does it mean? Well, this preserves the properties of the original distribution over this, and hence it is bounded by log of this, because that's the maximal entropy one can get. And that's it. Then we have all the ingredients. Q times log of the number of homomorphisms, which by definition is Q times H of X, because the entropy of X was precisely that, is bounded by this. Then this J is not playing any role, so it's simply the sum over this of P sub A times this, which is bounded by this by the previous observation, because H of this is bounded by log of this. And now we solve, no? So we leave number of homomorphisms alone. It will be 2 to the sum of P sub A divided by Q. But what is P sub A divided by Q? Is the value of the fractional edge cover, no? In this edge.
Is it homomorphism from H to G or G to H?
H to G, sorry. Yeah. Times this, and this is the productory? How do you call it? Product. Itatoria. Of this value to the fractional edge cover. And that's it. So it's essentially shielded, no? That's the proof. And that's all I wanted to present. It has nothing to do with my results. It has to do with some research that we do, but Tomago probably does much more than me. But I find it a very beautiful and you know, enlightening and inspirational.
This was like the most important result.
I cannot hear.
This was the most important result in databases now in the last 15 years.
It has sparked a lot of interest because it leads to optimal algorithms for joint evaluation. Yeah, worst case optimal
This
joint.
was the biggest revolution in practical algorithms and databases in the last 15 years.
Based on this result. Although the result, you can say that it was known, no?
Okay.
As it is. I mean, someone can say that this is Schiller's inequality. No? It was not known that it was optimal, probably. No? This was developed later. And what happens that when your graph is a database, then you have lots of constraints, no? For instance, you can say the number of edges linked to a person in Facebook is at most 5,000, right? So you can have a degree constraint on the number of edges coming on the degree of a node, right? And now, how do you encode this? How do you adapt the bound to be optimal, no? Because it's no longer true that it will be optimal because the graph, the graphs that construct the lower bound do not need to satisfy this kind of constraints. No? So then you can start refining this result based on constraints that you have on the size of the side of the data.
I have a couple of questions. I think they are related. So here we are usually assuming that H is the small graph and G is the big.
But we're not using that at any moment.
Yeah, I know that. But is it useful to consider the partition in the graph G when G is the large one and H is the small one? No, sorry. Here H should be the large one and G the small one.
No, here
it's confusing. According to the
H is the small. Is the small one. Is the
pattern. No? Reversing the
G is the template in your terminology.
Yeah. So H is large now and G is small. Is this useful, or you have to? Is it useful to make a partition in the always in the large graph and not in
in the large graph? Okay, yeah, that's why it's more conjective query evaluation than CSP with a fixed template. No?
So then in the H large and G small case, it is better to, in this last inequality, to use a partition in the edges.
Yeah, but I don't know if you can establish a relation in the other direction. Yes. Yeah.
But I don't understand the question. So it would be also counting homomorphism,
but from a large graph to a small one. And that's also...
So the bound applies, right?
But yeah, my question is it useful, or you need to change adapt something to make it a useful bound? That's it.
I haven't seen anything about this applied to CSP. No, because that's the case, you know? I haven't seen it. So my impression is that it's not very useful, but I don't know.
And weighted versions? That was my difference. Weighted.
Have you seen weighted versions?
Maybe constraints give you some.
Yeah. Constraints. That's definitely some kind of constraint.
That's powerful.
Yeah, but then. Then things become very difficult. Huh? So when you start adding constraints on the side of the data,
what is the size?
G is the data for me because it's large, right? H is the query, somehow, what you're trying the pattern, yes? For this kind of things, because weights in a way will be some kind of constraint. You will have to map this into it, but you will have to map this into an edge that satisfies, that has enough capacity to support your, yes? So it's a constraint in a way. Then things become, I don't know if this in this particular case, but in most of the cases, And this is when all these entropic bounds start to appear, because it's no longer clear whether the bound is optimal, and it's no longer clear how to compute it. In this case, you can compute the fractional edge cover, and you can compute the optimal one for your data. That you can do. But in more complicated cases, it's not even known to be computable. So that's when they have to approximate them with some computable bounds.
Are there any other questions?
Lo mejor así más el grano. Alguien se aplaudía así.
Una pregunta. Puede ser una pregunta, no, puede ser una pregunta un poco inocente, pero podría resultar útil conocer cuántos homomorfismos existen inyectivos o deyectivos.
Sí, claro que sí. Sí. Lo que pasa es que el número de homorfismos, bueno, un homorfismo inyectivo es un isomorfismo, ¿no? Claro. Y el número de isomorfismos se puede computar en base al número de homomorfismos, que son homorfismos sobre, en el fondo. ¿Sí? Así que eso, de alguna forma, esto no es que lo resuelva completamente, pero sí te da una cota, el número de isomorfismos. ¿Sí?
Pero contar como homomorfismo inyectivo, en el fondo los dos vértices no colapsan a uno, ¿se puede hacer con un truco de etiquetado como para forzar la...?
Sí, sí, sí. Sí, por eso yo digo, o sea, si uno quiere contar el número de isomorfismo, de alguna forma es como lo que hace es busca los subgrafos de tu patrón H, busca los subgrafos y cuentas para cada subgrafo el número de homomorfismo, y el número de isomorfismo es una combinación lineal de los números de homomorfismos de todos los subgrafos de tu patrón original. ¿Sí? ¿Qué combinación? Depende del patrón. ¿Había nada? No, parecía.
¿Alguna otra pregunta? No.
So what is the main advantage of the algorithm? The whole you said that it has an advantage.
It gives you the algorithm. The algorithm to yes. So what it happens is, imagine that you're evaluating. Typically, to evaluate this, you have a lot of joins, no, between the different variables, which in this case are the nodes. You want the intermediate steps not to give you very large answers. So you want the intermediate steps of the evaluation to be optimal as well, right? And this is what is achieved with this other proof. This proof essentially gives you the algorithm because it's an inductive proof. But it's also quite simple, but it's much more cumbersome to explain because you really have to. Yeah, it's not so clean to explain. Huh?
I don't understand it.
No, I do, but no, it is understandable. Yeah.
But the algorithm is easy because it gives you folders inequality, and then you just have a nested for loops that tell you where you restrict some parts. Then from folders inequality, it just follows. It's like you read how because join, you can think evaluating with fours that are nested and stuff like that. You read it from the proof, how the algorithm will look. This is not the best algorithm, but it is optimal in the worst case.
Yes.
¿No última pregunta? ¿Alguien? Bueno, demos las gracias de nuevo a Pablo.